Question 2. The photoelectric effect can be demonstrated by illuminating a negatively charged plate made from certain metals with ultraviolet light and showing that the plate loses its charge. Explain why, when ultraviolet light is shone on a positively charged plate, no charge is lost by the plate. Right, so if you imagine a metal plate here which is positively charged, if we shine some ultraviolet light onto that, then it may eject an electron. But if it does so, one of two things is going to happen. Either the electron's just going to fall straight back in because it's negatively charged, the plate's positively charged, and it'll be attracted straight back. Or even if it does leave, all it's going to do is, because it's negatively charged, it's going to leave an unbalanced positive charge behind. So it's just going to make this even more charged. So it will not lose any charge on the plate. So let's write that down. So if the UV ejects any electrons, they have negative charge so we'll only make the plate even more positive if they leave. Okay, so they won't be able to leave anyway because they'll just be attracted back, but even if they did, they'd just leave the plate more positive so it wouldn't lose any charge. Right, this next question is a very large question. It's a 6-marker. They're going to be assessing your quality of English in questions like this, and there'll be one per paper that you sit. The threshold frequency and work function are important ideas in the study of the photoelectric effect. Tables 2 and 3 summarize the work functions of 3 metals and photon energies of 3 light sources. Discuss the combinations of metals and UV light sources that could best be used to demonstrate the idea of threshold frequency and the idea of work function. Okay, there are a couple of things that I would suggest that you do when answering a question like this. The first is to try and summarize the information that you're given here in a better way. So I'm going to draw a little table here, and I'm going to have light source 1, 2 and 3, and I'm going to have these 3 metals: zinc, iron and copper, going down there. And if the photon energy is greater than the work function of the metal, then we'll get photoelectrons. So light source 1 is 4.0, zinc is 4.3, so that won't emit photoelectrons. But light sources 2 and 3 are both higher than that, so both of those will emit photoelectrons. For iron, these 2 won't, because they're both lower than that, and this one will, so that one's a tick. And for copper, the same, these 2 won't, and this one will emit photoelectrons. So that summarizes the information. Discuss the combinations best used to demonstrate threshold frequency and work function. So when answering a question like this, the first thing I would suggest is that we spend a little bit of time explaining what threshold frequency and work function are. So threshold frequency is the minimum frequency of a photon that can eject photoelectrons. Right, so short sentence to describe what threshold frequency, short sentence to describe what work function is. Work function is the minimum energy needed to eject a photoelectron. Now these two are related, of course, because the frequency of the light tells you what the energy is. So phi is equal to hf0, where that is the threshold frequency, h is Planck's constant, and phi is the work function. So they're both related to one another. If you know one, you can always work out the other one. So now we need to discuss combinations of metal and UV light source to demonstrate threshold frequency. So to demonstrate the threshold frequency, right, what do we need to do? Well, to demonstrate the threshold frequency, we need to show that some light that's below the threshold frequency does not emit photoelectrons, and light which is above it does. So we just need to pick one metal. I'm going to pick zinc, and show that light source 1 doesn't, and light source 2 and 3 do emit photoelectrons. So pick one metal, e.g. zinc, shine 1 onto it, and no photoelectrons will be emitted, comma, shine 2 and 3 onto it. You only need to actually shine one of these two, but shine 2 and 3 onto the zinc, and photoelectrons will be emitted. Why is this? This is because the frequency of light 1 is below the threshold, and 2 and 3 are both above the threshold frequency. Okay, so I think we've adequately answered the first part of the question, demonstrating threshold frequency. Now we need to demonstrate work function. Well, in this part of the question we kept the metal constant, we changed the light source. To demonstrate the work function we need to keep the light source constant and change the metal. So we need a light source where things are going to change. If we chose light source 1, then all of the metals we would get no photoelectrons. If we chose light source 3, then all of the metals would get photoelectrons. So we need to choose light source 2, because then we've got a difference here. So to demonstrate work function, use light source 2. And we need to shine it on at least 2 of these metals. One of them is zinc, and either iron or copper. I might as well do both of them. So to demonstrate the work function, use light source 2. Shine it on zinc, and because the photon energy is above the work function, then photoelectrons are emitted. Shine 2 onto iron or copper. And because the photon energy is less than the work function no photoelectrons are emitted. Okay, so how have we answered the question? Well, firstly what I did was I summarised the information that we were given in the question into a nice easy to see format. I then did a little bit of a talk about what these terms meant and how they were related. I then did a paragraph addressing the first part of the question and a paragraph addressing the second part of the question. And to answer a question like this fully, to gain access to all the marks, you need to write in paragraphs, you need to use sentences, full stops, and reasonably decent spelling and grammar. If you were to write in bullet points, you would not get access to the maximum marks for the question. But if in an exam you're running out of time, then you're going to have to do that anyway, just to get down as many ideas as you can in order to pick up some marks for the question. The last thing I'd like to just go over is wherever I said photon energy. Now notice I've said photon energy and they said photon energy here rather than just energy. Well, the reason for that is because it's very, very important in the photoelectric effect that each photon has to have more energy than the work function of the metal. It doesn't matter how intense your light beam is and how much energy it has in total. So if you had a really powerful red laser, its photon energy would be less than this, even though the total energy of the laser beam would be a lot more than any of these light sources. But still, it would not emit a single photoelectron. And that's because each photon in the really powerful red beam is incapable of ejecting a single electron. And they can't team up. So, because one photon interacts with one electron, the individual photons must have enough energy to emit electrons. And it doesn't matter what the total energy of the laser or the light source is, all that matters is the energy of the individual photons. Right. Now we're going to move on to question 2.3. Calculate the maximum kinetic energy in joules of electrons emitted from a zinc plate when illuminated with ultraviolet light. First thing we need to do is to think about the units. So there they've put in joules, here they've put the work function in EV. So let's change the work function into joules. So phi is equal to 4.3 times 1.6 times 10 to the minus 19. 4.3 times 1.6 times 10 to the minus 19 gives you 6.88 times 10 to the minus 19, and that is in joules now. So we've got the work function in joules. Next, we need the equation. So the photoelectricity equation is here on your formula sheet. So we have HF, that's the energy of the incoming photon, is equal to phi plus EK max. We need to rearrange that equation to get the maximum kinetic energy, so we need to move that over that side. So we get EK max is equal to HF minus phi, which is equal to H is 6.64 times 10 to the minus 34. Nope, got it wrong. Planck's constant there, 6.63 times 10 to the minus 34. 6.63 times 10 to the minus 34 times by the frequency, which is that number there, 1.2 times 10 to the 15, and take away this number here, 6.68 times 10 to the minus 19. So we need to do 6.63 times 10 to the minus 34 times by 1.2 times 10 to the 15 minus our answer from the previous question, and we get 1.076 times 10 to the minus 19. So that rounds to 1.1 times 10 to the minus 19 joules to two significant figures. Question 2.4. Explain why your answer is a maximum. Well, the work function is the minimum amount of energy required to eject a photon. That's if it's right on the surface. But if it was a little bit harder to eject the electron, then, for instance, the electron was lower down in the metal, then we wouldn't have as much energy left over to be the kinetic energy, because we'd have some extra energy to raise the electron to the surface of the metal, and then we'd need this much energy to boot it out. So we'd have less left over for the kinetic energy. So work function is the minimum energy needed to eject an electron. It might take more, in which case there would be less left over as kinetic energy. And that answers the question. I think if this were worth more than 1 mark, you would then go on to suggest why it might take more, and the reason for that is because an electron might be lower down in the surface of the metal. So if this is your metal and you've got an electron here, that one's relatively easy to get out, whereas if your electron's down here, there's your UV coming in there, you have to get it to the surface before you can eject it, and that takes some energy. Okay, that's question 2.